Hey, you're in space. Before you are the star Elongith and its planet Aphok. And you want to know the gravitational force of attraction between these two. In order to do that, you need to be familiar with Newton's law of gravity. So back to basics. When Isaac Newton got hit with an apple, he asked the most important question everyone has ever asked till then. If the apple falls, does the moon also fall? And guess what? It does. The moon does indeed fall towards Earth. However, it keeps missing it due to its higher tangential velocity, which acts against the gravity. That's also why its orbit around the Earth isn't perfectly circular, but more egg-shaped. By the way, Newton also came to the conclusion that two masses must attract one another, making the apple, as well as the moon, fall. So when Newton realized that, he tried to come up with an equation that describes the relationship between the moon and the Earth. And he came up with this: the higher the mass, the higher the pull. The higher the distance, the lesser the pull. Actually a lot lesser, due to the radius being squared. When talking about the radius, we mean the distance of the centers of both masses, rather than the surfaces, since the gravitational force on an object only depends on its mass, and not on its volume. I mean, this makes a lot of sense, especially since black holes exist. Okay, so Newton said that two masses must attract one another. But if that's the case, then why do you not get pulled to the teacher's desk when he brings a huge chunk of homework to the class? That's when Newton realized that there must be a really small constant in his equation, which makes the gravitational pull of small objects irrelevant. That's the g. However, it was just a placeholder, since he didn't have the measurements to come up with a constant. That's when Henry Cavendish pulled up a century later. With his instruments, he figured out that g must be around 6.67 times 10 to the power of minus 11 Newton meters squared over a kilogram squared. Okay, this means that you usually only apply this equation on bigger objects, like the moon or the Earth. But if that's the case, then why does the moon not pull the Earth? Well, it does, but only a little bit, since the Earth is way more massive than the moon. This gets shown when looking at where the center of mass is between the Earth and the moon. It's right there. We call it the barycenter. Both celestial objects rotate around the barycenter, but because it lies within the Earth, due to it being more massive, we perceive the moon orbiting around the Earth. Besides this, Newton also came up with this. Let's say our apple here is falling towards Earth. According to Newton's second law, which we discussed in this video, the net force is equal to the body's mass times its acceleration. Now, since the apple is falling towards Earth, the net force resembles the gravitational force. Matter of fact, the same gravitational force, which is also equal to gm1 m2 over r squared. So we can just cancel the mass of the apple and get the equation for the gravitational acceleration. With this equation, we can easily prove that Earth's gravitational acceleration is about 9.8 meters per second squared. Okay, so we know that the mass of the Earth is about 5.97 times 10 to the power of 24 kilograms. Its radius is about 6.371 times 10 to the power of 6 meters. And we already talked about the value of g. It's about 6.674 times 10 to the power of minus 11 Newton meters squared over kilogram squared. If we now plug everything in, we get about 9.8 meters per second squared. Alright, now we should be well equipped for our star problem. Okay, these are our nouns. We rounded g to 2 over 3 times 10 to the power of minus 10, so that we do not need to use a calculator. And as we discussed in the intro, we want to know the gravitational force of attraction, which is equal to gm1 m2 over r squared, as we learned today, so we can just plug everything in. Now, if you want to calculate this by hand, you usually want to separate the powers from their coefficient, so we get the following. Now we can just add the powers of a numerator and get the following. By subtracting both powers, we get our final answer of 4 times 10 to the power of 22 newtons.